In this video, we're going to talk about the second fundamental theorem of calculus. So the second fundamental theorem of calculus builds on the original or first fundamental theorem of calculus in that it takes that idea of a definite integral, so from a to b of f of x dx. Sometimes your upper bound can contain the variable x. So that would change your f of x to f of t, and you would have dt here instead of dx here. So those two things should match, that t, that x and that x. So let's jump right into an example. So let's evaluate this function. So let's say f of x is equal to the integral of cosine of t dt from 0 to x. And we'll evaluate that at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. So my first step in this process is to integrate as usual. So the integral of cosine is sine, but instead of an x, I have a t right there. So I'm going to input x first, so that becomes sine of x minus sine of 0, which is my a value. And that becomes sine of x minus 0, which is just sine of x. So you might realize that the second fundamental theorem of calculus really tells us that when you plug in x or some kind of thing with an x in it, that's a variable and not just a number and a number right here, that you're likely going to get out another function in which to plug in different rules. And so what that looks like when I plug in 0 all the way up to pi over 2, so when I plug in 0, there's nothing there. And when I plug in pi over 6, that equals 1/2. Pi over 4 is rad 2 over 2. Pi over 3 is rad 3 over 2. And pi over 2 is just 1. So in this way, we're really talking about an accumulation function. So like talking about plugging in another variable, instead of t, we have just sine of x. So the integral can become another function. So sometimes that's called an accumulation function because you can accumulate different areas under whatever curve you're working with. And as always, in theorem speak, if we want to define the second fundamental theorem of calculus, we say that f is a continuous function, and it's on an open interval, some I, and it contains a, so remember that's a constant, for every x in the interval. So if you take the derivative of the integral from a to an x value, you're going to get f of x, which we just saw. So let's put that idea into practice. Let's evaluate the derivative in respect to x from 0 to x of this integral of the square root of t squared plus 1 dt. So I realize that my f of t is that function, the square root of t squared plus 1. And so if I rewrite it in terms of the last slide, you don't have to. You can just recognize that if this is f of t, I just plug in x for wherever there's a t, because it goes from 0 to x. That would zero out the second part of the subtraction in the integral. So this thing is equivalent to essentially our function under there. Because there's a 0 there, please note, I just replace the t with an x. So it's the square root of x squared plus 1. Real challenging stuff. Something that comes from the fundamental theorem of calculus is something that we call the net change theorem. So if this is our fundamental theorem of calculus, which we know that f of x underneath the integral from a to b, so that lowercase f is really the derivative. Remember that uppercase f is really the original function that we can take the derivative of. It's just a rewriting, this theorem. So it's like saying if this is our original function, f prime of x, that same capital uppercase, all right, prime of x is just the same function right here because that's got to be the derivative. So all that being said, the net change theorem is this guy here. So we're just replacing the lowercase f with an uppercase f that matches this function and just calls it f prime of x. And of course, you can apply it to real-world functions. So if we look at this example, let's say a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is time in minutes, and that exists between 0 and 60 inclusive. So find the amount of chemical that flows into the tank during the first 20 minutes. So I like to think of it in terms of an original function and a derivative function. So if C of t is the amount of the chemical in the tank at time t, that means that the derivative, so C prime of t, is the rate at which the chemical flows into the tank. And that's something that we know. So if I write the integral from 0 to 20, because it's the amount that flows into the tank during the first 20 minutes, we can go from 0 to 20 of c prime of t, right, which is actually our 180 plus 3t dt. So I can take the integral of that and figure out what the actual amount is. And so the integral of 180 plus 3t is 180t plus 3t squared over 2. Plug in 20 and I get 3600 plus 600, and then I plug in 0, so it becomes minus 0. So the amount of the chemical that flows into the tank during the first 20 minutes is 4,200 liters. So using the net change theorem and the answer that we got, that was in liters, that actually represents the displacement of the actual amount. So when we talk about displacement, it's different than total distance traveled. So we've talked about integrals before in terms of the area of a graph when you add it all together. So things that are above the x-axis are positive, and anything below the x-axis is going to be negative. So that's going to represent the displacement of an object over time. So that doesn't necessarily mean that it is the total distance traveled. So an object or a particle or whatever it is can travel a certain distance, but that would become the absolute value of all those three areas. So note that the displacement adds up, positive areas above and negative areas below the x-axis. The total distance traveled would add up all the areas and just take the absolute value of those. So please note that those two things are different. So let's take that and solve a particle motion problem. So let's say that the velocity in feet per second of a particle moving along a line is modeled by this cubic equation, where t is time in seconds. So what I would like to find first is what is the displacement of the particle on the time interval from 1 to 5 inclusive. So from here all the way to there. So what that represents is the integral from 1 to 5 of vt, so that's velocity, right? So that is our first derivative, that's what goes right here when we talk about integrals. So I just replaced v of t with that equation here, this t cubed equation. So I'm going to take the integral, I'm going to plug in 1 and 5 and work out that magic and see what I get. Alright, so I have my integral here of this function. I plug in 5 and I get 25 over 12, and then I subtract. When I plug in 1, I get negative 103 over 12, and that gives me 128 over 12, which is actually 32 over 3. So when I talk about displacement, that tells me that this particle moves 32 over 3 feet to the right. So still sticking with the same problem, let's now find the total distance traveled by the particle on the same interval. So remember when we considered total distance traveled, we were talking about the absolute value here, and the graph is really nice because it tells me that from x equals 1, or t equals 1, sorry, to t equals 4, that thing is positive. So I want that integral, and I want to subtract the distance from 4 to 5, t equals 4 to 5, of that same equation for velocity. So same integral as before, right here and right here. But this time we're breaking it up between 1 and 4 and 4 and 5. So when you input 4 into this and subtract the input of 1 into this, you get 45 over 4. And when you do the same idea here, but inputting 5 and then subtracting an input of 4 from the whole thing, you get negative 7/12, which makes sense. So the area under this curve is 45 over 4, the thing in green, and the thing right here is in orange, which is negative 7/12. But when you consider that you need the absolute value, you want to add them together instead of subtract this negative bit. So it becomes 71 over 6 feet. So that models the total distance traveled by that particle. All right, that's going to do it for this video. Thanks for watching.